Hi, my name is Royce.
My name is Greg.
When we first started working on the Nini AI project, we were already knee-deep in augmented reality stuff. But we wanted to build something that enriches the lives of our users by solving an existing problem. We knew we wanted to build something with augmented reality, but we didn't know whose reality was best served augmented.
Yeah. While talking to some of my family members involved in medicine, we found that the most desired application of AR was in surgery.
When a surgery is booked, there are two main steps: plan and execute. But often, in the middle of the surgery, overwhelming information can hinder even the best of surgeons.
And if you're a student, the pressures of the operating room can be particularly daunting. But for both novices and seasoned professionals, practice to perfection is key.
Med students and doctors are expected to simulate surgery hundreds if not thousands of times before they are ready to lead the surgery room. No one wants a subpar surgeon, doctor, or nurse practitioner. And what separates success from failure is hours under supervision. CloudMD is your digital supervisor. Once you plan a surgery or maneuver, it monitors your technique and shows you just enough information to get to your next milestone. Small increments can lead to big successes. Let's see this in action. Here we are performing a culinary dissection. What we're going to be doing is parting a chicken. This involves setting up a set of events, aka planning a surgery, and programming what we consider success. In this demo, Greg is attempting to part his first chicken. And in the platform at the bottom, we can see our next steps. And at the bottom left, we can also see a heads-up display. At the moment, a screen monitor sitting at the kitchen counter is our heads-up display. But as AR glasses become more pertinent, with Apple's AR test kit coming out in 2022, we expect a miniaturization of this dashboard. Med students and doctors are always overwhelmed with info. To crunch this down, the active elements and directions that we are showing are simple to follow and non-obstructing. We use machine learning to train the elements and the parts of the chicken. We can track important elements needed to perform the following steps. And with tracking logic, such as slow tracking, we can make sure that if an element is no longer recognized, it is just hidden, like under a person's hand, instead of just disappearing altogether. In this demo, there are various elements that are showing. The next steps and the guidance that we're showing is the only information that is currently needed in the procedure. Even though there are many other steps in this procedure that are needed for success, what we have done is we have only shown the parts of the procedure that are relevant at the moment. For a medical student practicing something like a surgical maneuver, this helps them focus on their current problem at hand, instead of being shoved with a bunch of information that they wouldn't need at the moment. This kind of smart information processing helps train better physicians and also helps other people other than just surgeons and med students use this. It allows the upskilling of nurse practitioners and also the retraining of existing doctors to make sure that they're maintaining their skills. The accuracy rate and the percentage errors are simulated for now. But in a trial surgery or in a med student practicing on a gel body, they can set up parameters for errors and success rates. These boundaries that they set up can help determine how well they're doing. As you can see, the accuracy rate for now is dropping because Greg is performing parts of a surgery that weren't planned, and therefore the system thinks that Greg is going off script. As we are reaching the end of the demo, I would like to say that this software is heavily limited primarily by the training data. If you cannot find the elements, then you cannot perform the processes needed to make the software useful. What helps our software be successful is the fact that there are already mass medical imaging software that we can rely on. These sets of training data help us not only build more effective machine learning models to identify organs, methods, and tools, but to also figure out how they interact together. Our next steps include training for the human anatomy, programming a realistic surgical situation, and possibly migrating from a heads-up display to AR glasses such as the HoloLens or Magic Leap. Machine learning can help identify anatomical landmarks, and software can help guide the surgery, giving every student the guiding hand of experienced medical professional and real-time feedback that is consistent. This helps them train and become better doctors, surgeons, and nurse practitioners. Medical diagnostic tools and image processing already exist. We are building on top of that to create live tools to help doctors training for surgery and also possibly doctors in surgery. We're not there yet, but we're building the steps that we need for scale.